Okay, today we are going to begin talking about a subject called thermochemistry. And if you remember back to when we first learned the definition of chemistry, we learned that there were three parts to it. The study of matter, just the basic study of matter, its composition, what it's made of, etc. The changes that matter undergoes, so whether those be physical changes, chemical changes. And then the last part was the energy associated with those changes. And so in Unit 4, we're really going to focus on this energy piece, and that's where the thermo comes from. So we're going to really focus on the energy here for the next unit or so. All right, now as a quick intro, we got to first define several different terms. The first one being thermochemistry. Now, if you just look at it, obviously we can kind of split it into two parts, where you have thermo and then we have chemistry. Formal fancy definition is going to be the study of the transfers of energy as heat, which we're going to abbreviate as Q. I didn't get to come up with that one, but that's what it is. So the study of the transfers of energy as heat occurring during both chemical and physical changes. Now, when we talked about chemical changes and the indications that chemical reactions take place, one of our indications was that energy is released as either heat or light, which we saw with burning different substances. But the reality of it is that whether it be a physical change where the identity is not turned into something new, or a chemical change where the identity is turned into a new chemical, as we saw with the combustion of magnesium or other combustion reactions, or other chemical reactions for that matter, either one, energy is always transferred, even if it's a very small amount, and that's what we're going to focus on. Okay, a few more definitions. We are going to define energy as the capacity to do some form of work. Work really here, if particles are moving and things are being manipulated, then work is being done. And energy is always involved, again, in whether it be a physical, where the substance is not turned into something new, or a chemical change where it is turned into something new. But energy is always involved. And just like we had the law of conservation of mass, we also have the law of conservation of energy. And this is very simple. In fact, we kind of just substitute the word energy instead of mass, is that energy cannot be created or destroyed, and that energy is simply transferred in chemical or physical changes. It's always going to go somewhere. Okay, now for continuing with energy, there's two types of energy changes. The first one being what we refer to as an exothermic process. That's a process that is going to release heat into the environment. I always think of as exo, exit, the heat is being released into the environment. Typically, this is a situation where the substance feels warm. Not all the time, but very often. Now, endothermic is going to be just the opposite. This is a process that absorbs heat from the environment, or it uses energy. And typically it feels cold. The ice packs, chemical ice packs that you have where you crack the liquid inside and you shake it, that is a chemical reaction that is endothermic, and it absorbs the energy from the environment, therefore making it feel cold, okay? As opposed, for an example of an exothermic process, if you've ever used those hand warmers or feet warmers, there's a small chemical reaction that's going on inside of those that also is an exothermic process that is releasing heat. So the first thing is just the flow of energy, and exothermic if it's being released, endothermic if it's flowing in. Also, if we define kinetic energy is the energy of an object that's due to the object's motion. Kinetics usually refers to movement, and so again, this is the energy associated that is due to an object's motion. And we're going to talk a lot about particle motion in this section, as well as a reflection of kinetic energy and temperature. Which leads us to our formal fancy definition of temperature. Temperature is simply defined as the average kinetic energy of the particles in a sample. So, as kinetic energy increases, so does temperature. Okay, and this is going to be an example of a direct relationship, meaning as one goes up, I'm going to try to get this to a different color here, see if this works for me. And we saw this before. If it's a direct relationship, as one goes up, the other goes up, or as one goes down, the other goes down. If you were to graph that, remember we've seen this earlier, if you have a graph of something that's a direct relationship, it's going to be a straight line with a positive slope that's going to go through the origin. Not really a completely straight line, but you get the picture. So that's going to be a direct relationship. So if particles have more kinetic energy, their temperature is going to go up. If they have less kinetic energy, their temperature is going to go down. And there are 3 temperature scales that we see on a somewhat regular basis, that being Fahrenheit, that we're the most familiar with, Celsius, that we use very frequently in chemistry, and then also Kelvin, which is really what we're going to use the most in chemistry, and I'm going to explain that on the next slide. So again, temperature from our perspective is simply an average kinetic energy of the particles in the sample, and we'll spend a lot of time talking about that. Alright, so the Kelvin temperature scale was developed so that there could be a system that had no negative values. Later on we're going to do some calculations with temperature. It's going to make it just a lot more difficult if we have negative values. And so Kelvin and Celsius essentially have the same intervals. It's just Kelvin does not have a negative value. It starts at what would be negative 273.15 degrees Celsius, which is also what's called absolute zero. Absolute zero is a temperature at which particles literally are not moving. No motion, and it's almost impossible, or absolute zero has not been reached here on Earth, because there is always some energy that's flowing into a system. Sorry, let me back up for a second here. Okay, and that's our start for Kelvin. It's 0 degrees Celsius. To do the conversion, it's very simple. You only have to add 273 to a temperature value for degrees Celsius. So for example, if I started with 10 degrees Celsius, I wanted to convert it to Kelvin, I just add 273. And just as a side note, when we talk about the Kelvin temperature scale, we don't say degrees. So although we would say 10 degrees Celsius, we simply say 283 Kelvin. It's kind of a formality thing. But if we were doing the opposite, if we wanted to go from Kelvin to Celsius, well, we just simply do the reverse. So if I had 293 Kelvin and I wanted to go to Celsius, I simply would subtract 273, and I would be left with 20. I'm going to put the decimal place there for significant figures, and this would be degrees Celsius. So much easier conversion than canceling out units. Okay, so now we're going to talk about heat. And heat we are going to define as the energy transferred between samples because of their differences in temperature. Heat has an abbreviation of Q. And one of the things about heat is that it will move spontaneously from matter with higher temperature to lower temperature until thermal equilibrium or an equal temp is reached. And I know that sounds really hideous, like a big, long, ugly definition, but we've all experienced this. If you've left a drink, maybe a cup of water that has ice cubes in it, okay? Well, what happens, do my 3D version here. What happens over time, as we know, is that the ice melts. So if you think about heat flow, the ice is essentially absorbing all of the energy from the liquid, and it's going to slowly melt, and eventually you're going to end up with liquid that is all the same temperature. So although this sounds, ugly and scientific-y, I don't know if that's the right word, but we've all seen this happen, okay? When something sets out to room temperature, that's all that happens, is that the heat is flowing from something that has higher temperature to lower temperature until it's reached. And one thing is that we always talk about heat flowing and things gaining heat or losing heat, as opposed to things getting colder. It's kind of just a perspective thing. And it goes along with referring to something as endothermic or exothermic. So the ice cubes here would be absorbing heat from the environment, or undergoing an endothermic process in order to melt. So we'll talk about that a little bit later in the unit. Also, heat cannot be measured directly, so we use temperature as a measure to track the transfer of heat. So we'll look at how temperatures change over time between substances in order to measure heat. And typically when we are going to talk about energy for this unit, we're going to use the unit of joules. Very frequently you see the term kilojoules used, and this is going to be the same ratio that we've seen with our kilometers or kilograms, and the fact that 1 joule is going to be equal to 1000 kilojoules. So again, we see those metric prefixes sticking around and not completely going away really ever. So, okay, now just as a little bit of a reminder, the same thing, a lot of it in thermochemistry is perspective. Whenever we talk about change in something, you know, from beginning to end, this little symbol right here, this triangle, this delta sign, means change. And whenever we're finding the change, whether it be the change in energy, the change in temperature, it's always the final value minus the initial value. And it helps us in terms of signs. So for example, if energy is flowing out of a system to the surroundings, we say it's going to have a negative sign. And again, this is going to be an exothermic process because the energy is flowing out of that system. Okay, so if this was a chemical reaction that was producing heat, it's flowing, it's all from the perspective, oops, let me back up here. Okay, it's flowing from the system out, that's exothermic. If a system is gaining energy, it's going to have a positive sign, meaning it's going to be absorbing energy from the environment in order to get back to reaching that thermal equilibrium. So again, those chemical ice packs, okay, the reaction is absorbing energy, okay, it's endothermic, and it will continue to be endothermic until, if you let it sit around long enough, it eventually gets to room temperature, and the system is all equal and it's all reached thermal equilibrium. Okay, now again with heat, the way that we measure this is using what's called a calorimeter. This is a reaction container that's surrounded by water. We are going to, this is also where the term calorie comes from, because even in food calories you're talking about how much energy is stored in that food, and so a calorimeter is going to measure the amount of heat that is gained or lost by a system. And the energy given off during a reaction is equal to the energy absorbed by the water. So what we say is that the energy absorbed by the water is equal to the energy released by the substance. And we're going to do some labs where we get to burn some food to figure out how much energy is stored in them, and I think it really helps make this easier to understand at that point. But two of the setups for the types of calorimeters, and there's a couple of different ways with which to do them. The one on the left we're not going to do. This is what is called a bomb calorimeter. I know probably you guys would find that one more exciting, but essentially what you have is, this is a situation where you need ignition wires, and you are igniting a reaction that's going on. This would be whatever your material that you are combusting is going to be reacting. This is going to produce heat. The water is going to absorb that heat, and then you're going to be able to measure the temperature change with the thermometer. So that's a bomb calorimeter. We're going to use a standard, pretty much, simple setup of a more traditional calorimeter, where we're going to have a reaction that's going to take place. Sometimes it occurs in solution. We're actually going to have run something where we burn something underneath water, and the water that absorbs the heat will measure it that way. But more importantly, you're still measuring the temperature change with a thermometer, and that's going to be a reflection of how much heat was gained or lost by that system. And so I'm going to go ahead and pause here, and in the next video we're going to talk about specific heat and do some math problems related to specific